7 o'clock. So evening, everybody, and welcome to this evening's Whitechapel Lecture, one of our occasional series of lectures. We have three or four perhaps a year, when we come together of an evening and to hear an interesting topic. Tonight's speaker, I'm just delighted to say, is Stewart Williams. And Stewart is technical director and one of the founders of WAAM 3D. Originally, he did a physics degree, then worked for an SME involved in lasers, and then nearly 20 years at BAE Systems. But for the last 15 years, he's been at Cranfield, where he's the director of Welding and Additive Manufacturing Centre. And of course, that's where WAAM 3D comes in, because they are a metal additive company. So Stuart's going to tell us about both about the technology a little bit and its application, but also about how the company came into being and what it's like setting up a company, which I think will add an additional dimension to the discussion. I would remind everybody that we are recording the session tonight. So just be aware of that it is being recorded. If you don't want to appear, obviously, at all, then just turn your camera off. We'll be handing over to Stewart in just a second, and he'll sort of share slides and go through the presentation. And at the end of the session, at the end of his talk, we'll give the floor over to some questions. You can obviously either use the chat function for that. If that means anything to you, it means you can type your question in there, or failing that, we'll try and have a bit of a discussion afterwards, and I'll try and come to you, so make yourself known, wave your hand or something if you want to ask a question. So I think without further ado, I'll hand over to Stewart, who will share his slides and give us tonight's lecture. Stewart.
Thanks for the introduction, Pam, and good evening, everybody. Thanks a lot for the opportunity, actually, to talk about what we've been doing. Actually, we've been at Cranfield now for nearly 20 years. I'd say 15's a bit out of date. So I'm going to talk to you about our journey, really, from taking a technology from nothing, effectively, through to full commercialisation, and a company providing the technology to industry. As Pam mentioned, I'll highlight first of all about some of the technology aspects, and then I'll talk about the company and what the company does, and then towards the end I'll just summarise really some of the challenges that we faced on the way. Let me know if you can't see that. So, as I mentioned, we're taking the technology from an idea to commercialisation, which we started back in 2006. So I'll just briefly introduce what this directed energy deposition additive manufacture is. It's a bit of a mouthful, but that's what the standards bodies have called it. A little bit about the first opportunity in the project, and then how we put in place an industry program, an application program, then the setting up of the company and the challenges that we've faced. So when we started, the motivation really was to replace or improve the existing manufacturing methods for metal structures. So a lot of it, of course, is machining from billets or forgings, which is incredibly wasteful, actually. So in some applications it can be as much as you buy 100 times more material than you're actually going to use in the application. And especially given these days, it's not only economically very bad for the industry, it's also, of course, not very sustainable. Alternatively, we have some fabrication methods which have some complex supply chains and skill shortages, and actually is rather hard to do. And similarly with casting, we have long lead times the properties are not really as good as we would like, and we have fixed designs unless you need more tooling. So in essence, wire-based directed energy deposition is rather simple. Effectively, we take what you might consider as a welding robot and power source, and we're using wire as a feedstock, and we build the structure up, in effect, what is weld metal. Actually, it's a bit different to weld metal because the thermal conditions are different. And then we program the robot to deposit it in layers. As you can see in the video, this is a simple example that we did for ARA at Bedford. It's a wind tunnel model, which was to be made out of maraging steel, which is very difficult to machine. And we built this using this 3D printing method, and we were able to make a hollow structure so that the sensors and so on could be put inside. So what is the motivation for this? When we started, the main motivation actually was just to reduce the cost of manufacturing. And this is primarily through better material utilization. So typically we might achieve a cost saving of 70% compared to machining from solid. This is for materials like titanium, high value materials. And the second aspect is about lead time reduction. Many aerospace parts in particular are made from forgings, which can be maybe 14 months plus 4 months for machining and finishing. And using this 3D printing method, we can reduce this from many months or years to weeks. And we also have the possibility of improving the parts properties using multi-materials and new designs and hybrid processes. And if I go back to when we started, my background actually is in aerospace manufacturing. If we look at the utilization of materials in aircraft structures, in the 747 it was 83% aluminium, but the 777 was 68% aluminium. By the time we got to the 787, of course, this had been almost half the aircraft is now made out of fibre reinforced plastic. And there's an issue that aluminium is incompatible with carbon fibre composite due to corrosion. So they couldn't use the aluminium where it was in contact with the composites. So our titanium amount in the aircraft had gone from 4% to 15%. And in a typical 787 at this time, around in the early 2000s, there were roughly $20 million of forgings on the 787. And given that the cost of material was round about, or still is round about actually $50 a kilo, if you're machining most of it away, this is a very expensive method. So we set out really to talk about whether we could develop a large-scale additive manufacturing process for manufacture of actually rather simple parts. So we're not looking at complexity here from the additive manufacturing process. And you can see some examples of the target applications that we had. When we first started, we used a particular process. There are many variations in processes, which I won't go into today. And we built this first part in an afternoon, took 3.5 hours. It was deposited rather nicely, and we thought, well, this is pretty good. Of course, it turned out to be much more complicated than we thought when we tried to make Class 1 engineering structures. So we spent a lot of time looking at the intricacies of the process for building complicated parts, looking at things like intersections and crossovers. It's not like machining, of course. In machining, if you go over the same area twice, it's not a problem. It certainly is a problem in additive manufacture because you'll have twice as much material as you need. And we looked at whether or not we can deposit, whether we always had to deposit vertically. So we investigated depositing at different angles and found we could actually build structures horizontally if needed, and therefore we could make enclosed sections. This started in 2006. As was mentioned, my background is physics. Actually, it's not welding or metallurgy. So we spent a lot of time looking at the physics of the process and understanding it properly before attempting to make complicated parts, which was what, of course, all the industry partners were wanting. This is the very first complicated part we made in steel. You can see it in the tool, and it was reasonably successful. Then when we moved that forward to titanium, we found lots of different problems. In particular, we had issues with cracking in certain areas. We had to work out how to deal with the intersection, how to manage corners better so we didn't get cracks and so on. So when you translate this rather simple concept of icing a cake with metal, it becomes much more difficult once you try and do anything useful. However, we then went on to build many other parts. This is just a few examples here. So the one on the left was a part we made for BAE Systems a long time ago now. And then the ones in the middle are large-scale turbine blades for GE. And the one on the right is an oil and gas part. It's quite a simple part, as you can see, which is just an Inconel transition section. But these are actually rather difficult to manufacture in practice. And because we were working with many companies, every single company wanted their own parts manufacturing. So it can be from these rectilinear parts. This is a double-sided part for Airbus. This was a complicated part we did for GKN and Boeing, where they were evaluating the technology. This thing looks rather simple, but is actually rather difficult. It's an elbow section. And this is because we need different layer heights inside to outside. We made a 6-meter part. This is looking at the issues of scaling, for example. A lot of impeller kind of structures and different materials. And the lady you can see in the picture is responsible for manufacturing most of these parts, actually, and was fundamental in the development of the technology. In parallel with this, I haven't included it in this presentation. I'll answer the question now before it's asked later, but in terms of material properties, we can get better than wrought material properties. We can introduce cold work to improve the properties, and also we have faster cooling rates than you get in forgings, for example, and more uniform structures. So the industry partners were extremely interested, but of course this was all being done in the university laboratory. So when that program ran out, we then collected all of the projects we had and put it together into a program, or a rolling, what I call the rolling technology program, to mature the technology to TRL9 so that it could be adopted by industry. We also needed to generate industrial interest, because at this point in time, everybody thought additive manufacture was just powders. It's far from it, actually. These techniques that I'm describing have been known about in the welding field since the 1920s, which was when the first patent was put in. But actually, no industry partners knew anything about it. The first question I was always asked was, why aren't you using powder? And the second question was, why aren't you using a laser? So we needed to make industry aware of the technology and also support them with business case evaluations. But the most critical aspect actually was to establish a supply chain. So it's all very well having this in our laboratory, but actually where could they buy it from at a commercial level? So as I mentioned, to get the critical mass needed to enable this to all happen, we put together all of our activities into one block and invited industry to sponsor the program, which we managed to do. Those numbers there are a bit out of date, actually. But we collected together different kinds of projects. And because we had many projects, of course, we then managed to get a critical mass of effort. Currently we have about 34 people working on this technology at Cranfield, a mixture of academics, PhD students, researchers, and so on. And because we can't do it all, we have academic partner universities working on materials and performance and in-process NDT, various other topics that's not our speciality, but brought them all together into the program. So at the moment we have probably about 80 people in the UK working on the technology. And over the years, we've had maybe 20 to 30 companies directly involved, and many more at a lower level. And actually, you might think, okay, well, I just get my robot and welding power source and then deposit it and test the material properties. But if you really want to take a technology through to full commercialization, you have to address all aspects. So the technical program was rather broad. I split it down into system development, materials, and design tools. So without going through the details, of course, the critical aspect was the processes themselves. So we have many different variants that we were developing with higher build rates and better fidelity, and how to control the shape is a critical aspect. And then these are other processes such as cold work, hybrid manufacture, integrated NDT, and so on. We needed to develop a whole load of hardware. So welding equipment is not suitable for additive manufacture, really. It's only designed for doing short, low duty cycle work. We had to develop how to feed wire properly, introduce local shielding, process monitoring, looking at different platforms, wire preheating, and so on. Equally important, and probably more important now in the company, is the software development. This is about path planning, control software, simulation, management of the data, generation of process parameters, and so on. So once we had all those, of course, we can then provide commercial systems and a mature technology, if you like. But in reality, you need to, in parallel, develop the applications, which you do through working on materials. And you can't imagine the number of materials that we've worked on with this technology, ranging through from aluminium lithium. Of course, the primary one was titanium, lots of aluminium alloys, nickel super alloys, low carbon steels, high performance steels, and indeed refractory metals. We've done titanium and tantalum, for example. And these all need to be characterized in terms of a broad range of performance characteristics. And only by doing that can we get qualified materials that can actually be used. And then people needed to know how to use all this equipment and design for it. So we had a lot of design tools, CAD to CAM, knowledge expert systems, LCA tools, how to do tooling design, and so on. So you need a big team, but only by doing all of those things can you achieve industrial applications, which is where we were always trying to get to. In terms of the supply chain, we tried to partner with a range of different companies, such as system integrators, robotic companies, and so on, because we didn't really want to get into the business of manufacturing systems. But actually, it seemed to be impossible. So in the end, we just set our own company up, which is WAAM 3D. And these are the three founders: myself, Dr. Martina, who was going to be giving this lecture, and Dr. Jiao Ding, who's the Chief Technology Officer. So I can say actually both of them started with me as master's students, then PhD, through researchers and lecturers and so on, through to the company. So just to say a little bit about the company and what it does. This is the timeline, actually. So here you can see this work was started in the 1990s. We then had this preliminary program, and then we started the maturation program, founded the company in 2018. We got a Series A investment in 2019, actually right at the end. And then we started trading in January 2020, which of course wasn't the best time to start trading as a new company. And then we spent a lot of time growing the company from then until now over the last 5 years. We were successful in developing a new wire composition, which we're able to supply to Relativity Space in the US, which helped us with the rapid rate of growth that we managed to achieve. And you can see we went from 3 to 10 to 15 staff to 30. And we then set up also a Singapore, a JV in Singapore with our investors for manufacturing of parts. And then we had our Series B investment at the end of 2023. We now got 42 staff. And then last year we completed the initial requirement that we had for the product portfolio. And you can see we have many customers along the way. So to give you an idea what the company does, it sort of matches the program I showed you earlier. So we have the hardware. So this is the actual systems themselves, and we have 3 or 4 variants of this now. And then all the software. So we have a large software team for path planning, for allocation and management of process conditions, simulation, and the in-process control. And also we provide specialist high quality wires. And then we support the customers with business case development, training, how to manufacture parts and special products. So we do have competitors who just provide this bit actually, but we believe that the customer needs all of this to be successful in their application. To give you an idea what the commercial system looks like, this is the outside of our first product, and inside we have a protective environment and then a robot and a part manipulator. And take that off, you can see the robot, and we get to the heart of the system, which is a part manipulation system. And then the critical part, of course, is this end effector, which has various things in it. So this is the torch and the wire feed system. This wire feed positioning is critical, so we have automated wire positioning. We measure the pre-deposition temperature and the post-deposition temperature. This is needed to ensure the microstructure and properties. We measure the shape, which is also essential, of course, to ensure that we have material everywhere we want it. We have a local shielding system, so that for building very large parts in reactive metals such as titanium, we do not need a very large enclosure. We have a camera for monitoring what's going on. And then we've subsequently released further variants. This is the last one that we released just a few months ago. And this is based on a new process that's been developed in the university. So we have a continuous flow of technology developed in the university through to the company, which is extremely beneficial, of course, for the company, but is also beneficial for the university because we have a commercial route to make sure the research that we deliver has high impact. And this system is based on a much higher deposition rate process. So with this system, we're depositing 15 kilograms per hour, and we can build parts up to 3.1 tons. And then at the other end of the scale, we have what we call a mini WAAM. It's not so mini actually. The build volume is 0.6 by 0.5 by 0.5, but it's transportable, fully enclosed, and it's primarily focused on materials development and research. So it has multi-wire and multi-material capabilities. So there's a couple of examples of what we've done with this CW MIG. This is some of the latest parts. This part here represents as part of a launch vehicle. This is a big application for this technology. We're currently discussing with a Japanese company about setting up a manufacturing capability for large-scale launch rockets for satellites. And critical here is we can deposit very fast at 2.3 kilos an hour. So this one here is 100 kilos, so you can work out that's roughly 20 hours to build this part. Then looking at other industry sectors, this is the energy sector. This part here is 100 kilos, and we're able to build that in less than a day. On the software side, it includes business case and life cycle assessment. And here we can compare conventional manufacturing with the WAAM process. both in terms of the energy consumption, the emissions and the cost. And our customers always need this information to be able to evaluate the business case. This is path planning software. I'm not going to let this video run because I don't have time to go into the details. I might need to change my pointer actually. So this is all about how to program the deposition path and the details around that. And you need these tools to enable customers to be able to design their own toolpaths. In this case, it's a multi-part on a curved surface. As you can imagine, this is not a trivial thing to try and plan. On the control software side, so we need much higher levels of control and monitoring for industrial applications. So we developed this control software, which you can see here. We're monitoring a lot of the process parameters. We're also monitoring in this case, the wire position, the lead temperature, the oxygen level, and so on. And we can set up response levels and user notifications. These are all the different parameters here. And if anything goes out of range, then this will be notified to the operator, and of course can be used for data logging in a digital passport. Another example of something recently transferred from the university to the company. This is automated wire positioning. So what you can see here, this is the gas metal torch, this is the arc, this is the wire. You can see the melted end of the wire here, and this is the melt pool. And to keep a stable process, the separation between the wire and the melt pool is critical. And so we're using AI segmented video, and we're identifying the critical points and tracking those. And this means we can now adjust the wire position real time, 15 frames per second, and ensure good quality of deposition. And then you can see when all this is running, all these things are being monitored. You can see the wire position changing here. This is the wire position diagram, and this is the actual process. In this case, you can see actually we're using a dual wire process. Now we have the two wires being deposited simultaneously. And this is all logged around the build of the part. So we also had to develop a very specialized wire that has much higher quality than standard welding wire. So you can see actually this is building a part, and we go from our very nice wire to another wire. You can see the change in geometry. Similarly, you can see the change in build quality, and these wires nominally fit the specification, but actually the one on the right is not suitable for AM. Training is vital as well to enable the customers to use the technology, and we can provide that at different levels. So this can be from the process fundamentals to the operation of the machine to the WAAM engineering, which is basically how do you build parts, and then specialized training as well for things like tooling design and so on. Just looking at one or two applications. This is a pressure vessel for a satellite application. So this is 65% shorter lead time and 40% cheaper. We're using 200 kilograms less material. So this is an example of where it normally would be made from a forging, but actually there's only 12 of them needed for the mission. So being able to do it by 3D printing is highly beneficial. This is an early example that we took through for qualification. This is a similar kind of thing. This is a satellite propellant tank, and this is normally made from a forging this thick, around 35 millimeters thick. And what we're doing is producing a near net shape preform. And you can see the process here. We're operating in a tent for an argon environment for this particular case. This is plasma deposition. You can see the thick section here, and you'll see in a moment that we're going to build vertically, and you can see a bit more clearly what's going on. And we're changing the process conditions as we go. I mean, it looks like a bit like pottery. And it has many of the same characteristics, but it's a bit more difficult with liquid metal. So we then, of course, needed to test it. So we get it machined. This is an X-ray CT image, an X-ray image, sorry, of the part. There are no defects in it. It was then tested and compared to the forged part and performed identically, even as far it was tested to failure, and the failure mode was identical to the forging. So this gives us a 50% cost saving, the lead time reduced from years to weeks, and we can have a specific size of tank for each flight instead of the predetermined ones based around tooling. This was a very large part we did for BAE Systems. This is the Eurofighter Typhoon rear frame that supports the engines. This is roughly 2.5 meters across, and again is normally made from a massive titanium forging. So we now benefit between the university and the company by running what I call an integrated technology program. So we have at the bottom here the TRL levels and the MRL levels, and of course the university operates in this space down here, carrying out research and innovation. We then develop solutions which we then partner with the company to do the technology development needed to get this more mature, both in the terms of the technology and the manufacturing readiness. Then it can be taken forward by the company to industrialization of products, and of course then provided to the customers. And then we get the feedback from the customers about the requirements. And actually this model is very popular with industry, because we have many projects now based both in the university and the company, whereby they're developing specific application here. We may be developing materials and properties and microstructure and so on, and they can get this very quickly. It's just showing the people involved. So in terms of the challenges at the university, getting the critical mass funding is of course the main challenge, and there's a constant need for research funding to support the multi-year multidisciplinary program, and there's literally been hundreds of projects. So I've just listed here, for example, we have had three EPSRC programs, 2 Innovate UK, 4 EU. Mostly, although we have many industry funded projects, and this is all supported by 30 PhDs and 100 or so masters and research projects. Overall, we've had probably 20 to 30 million to support the development of this technology. And then in terms of people, getting enough good ones is a real problem, as you might imagine. What we're doing is not trivial, so we really need high quality people. And I must point out that we virtually have none from the UK. It is a major problem. And then actually in the university environment doesn't really encourage team working within a team. It's quite competitive. So actually setting up the whole centre to ensure the team is working to a common goal, which is not so common in the university, was something we needed to implement. And of course, more recently, we've now got the introduction of some significant geopolitical issues from our perspective, because all of the best, I have to say, most of the best engineers, not all, have so far come from China. And of course, now we can't get them. So the result actually is that we can't do the work. And in fact, we've tried to implement projects with people from China, and actually they've ended up just doing them in China anyway. Another challenge is growing the facilities. So we started off with one system. We now have 12, but actually finding the resources to build up the facilities to support this number of projects is also a major issue. And then the ongoing continued maintenance and upgrade of these. Balancing the academic and industry needs. So there was a big industry drive, still is a big industry drive. We do need to do, I wouldn't say there's a need to publish lots of papers, but it's more about doing the work with a proper scientific and academic rigor, whilst keeping the industry partners sufficiently happy that they're okay with the progress. And we had a big range of industry sectors and often competitors within the same sector. So managing all that was always something that needed to be taken account of. So we had to deliver this complex program with many stakeholders. Looking at the company aspect, well, of course, as with any startup company, the major challenge is around cash flow and investment. So there was a desire to grow the company, which is normal, of course, for a startup. It took us 18 months to get this two-stage Series A investment. So Acuron, who are our investors, are not venture capitalists at all. They are actually, they're owned by the Singapore government, and they're used for acquiring technologies. And they wanted to be the first to be able to provide a combined additive subtractive solution. They already do aerospace machining, and so they wanted to get involved in the best 3D printing technology. We then needed to get a Series B investment as normal, and actually this was in the period 22 to 23, which was very difficult due to the downturn from the COVID episode. And we couldn't get an independent investment, which was really what we wanted. So we eventually, this investment was provided by Acuron again, who are now the majority shareholder, which wasn't really what we wanted. It wasn't really what they wanted either, but that's where we are. And then we're now looking.
You're going to get your thing done.
We're now looking for Series C investment. So we've done our major product development, and we want to grow and expand the market. We did have a change of business strategy, which didn't really help us. This changed after 12 months. This was because originally we were partnering with companies to provide the systems and hardware. That wasn't our specialist area, but we found out at an early stage, A, that we needed to know everything about the system to be able to provide them to customers, and B, that actually the people making the systems were making more money out of it than we were. So in the end, we decided to build the systems ourselves, and that requires more people and especially capital needed for the growth. And it's always been a challenge getting good quality technology transfer from a university environment into a commercial environment, and that's an ongoing thing. So in summary, I would say we pretty much addressed most of the problems around industrialization, and we would say that we've taken the technology from TRL 1 to 9. We have set up the company to provide the supply chain and the full technology solution. I'm not going to talk about it today, but the last major challenge actually is, and one of the barriers to widespread adoption is the expense and inflexibility of the current qualification approach, which we are now addressing through a new program in the university. So thank you very much for your attention. I was happy to take any questions.
Thank you very much, Stewart. I mean, I suppose I'd perhaps counter some of the statements you made at the start in terms of flexibility of casting, because I mean we do use 3D now, so it's not always, you know, extensive for needing tooling. We can actually print sand molds and print and actually machine molds as well from solid. So perhaps some of the stuff around the time scale for castings, I'm not sure whether it's the same in forgings, but certainly in castings, you know, we can do quite rapid turnarounds now, and you know, for small series runs as well. I'm sure Mark could fill you in on some of that as well. No, very interesting. So I'll open it up to the floor. I can't see any comments in the chat, but does anybody have a question they'd like to ask at this stage? Put your hand up or wave or something if you want to ask a question. Mark, is it you unmuting because you want to ask something? Yeah.
Stewart, thank you very much. I'm talking to you not as an engineer or a metallurgist, but I teach in the engineering faculty at Birmingham City University. And one of the things I was brought in to do was to bring geopolitics, business and team working into every module we teach.
All right, good.
And looking at building effective teams and working with industry, rather thinking, what do industry want to see coming to them from universities, rather than us just churning out graduates hoping they'll find jobs. So I'll send you, if it's okay with everyone, Pam, will we have the slides for Stuart's contact, what we do at BCU. I leave actually this May, but we're looking at block teaching modules and bringing an industry component into everything we do. And everything is built on teamwork. So each student becomes responsible for each other's degrees rather than being competitive against each other, which brings I think a more employable student at the end of the process. Just I sort of picked that up straight away from your talk.
Yeah, I'm glad to hear that. Yeah, very good.
Yeah, I was thinking exactly the same when Stewart was talking, Mark, thinking about the approach that Birmingham City University is taking now to try and make a more module and a more industry focus. So they're very keen, aren't they, on getting the teamwork in and getting the students to be working on real life projects that are going to be valuable to them, but also valuable to industry. So that's well worth a follow up, I think, as well.
I mean, just to comment on this.
Yeah.
So, with our master, we don't do undergraduates at Cranfield, of course. With our master's courses, we do try to encourage a bit of this. But I'm not just referring to the students, actually. I'm also referring to the research environment, which is also highly competitive. And we could really benefit by having a more collaborative teamwork approach within a particular university.
Well, I have to comment there. Sorry, Pam, after you.
Well, I was just going to say, I was going to agree, but also say that it's not always easy to get industry involvement to come up with the projects, which, so all parts of this jigsaw need to come together, don't they? So that industry liaison is really important. And it's, industry is busy, but they need to take time to come up with projects and to engage with the universities, don't they? Particularly like say BCU and Cranfield, where there are opportunities to get projects done. Sorry, Mark, over to you.
Oh, well, to build on that, Pam, we work very closely with Jaguar Land Rover on this model because they're a very nearby large employer. And the other challenge I've also had to teach my academic colleagues about the same thing. So it's not just students; it's a cultural change that's needed within universities, I think.
Yeah, that's interesting, and I guess you'd agree with that, Stuart. I mean, I think Cranfield have always been pretty good on the industry links, but perhaps you want to comment on that industry liaison part of the piece.
Yeah, certainly. I mean, I would, just as you picked up on the casting point, I would pick up on the industry point that I worked in industry for many years, and actually, it's not about industry coming with projects; it's about industry and academia coming together to tackle problems and then come up with projects that are needed to tackle the problems rather than one going either way, if you see what I mean. Yeah,
it's a good point actually, because I say it's about the understanding, isn't it? A two-way dialogue rather than just presenting a problem or presenting a team of people who might be able to solve a problem. You need a sort of a dialogue. Yeah, it's cultural change, isn't it, really?
Yes.
Yeah. Just pause for a moment, see if there's anybody else who wants to jump in as well. Yeah, okay, yes.
Yes, Alan Ewart, very, very interesting. I was just intrigued, going back to my many aeons ago, welding sort of experience, when clearly a key part of the technology of developing welding is the composition of the wires. So if you're making and I noticed it was there, the classic 96.4 titanium alloy. Is the wire actually 96.4, or do you have to amend the chemistry in order to deposit 96.4?
Well, actually, I would make a point more generally that indeed welding wires have been developed, but actually, what we often get asked, so take titanium as an example, what the industry asks for titanium 6.4 to replace a forging, but actually the microstructure and the properties of what we deposit are nothing like a forging. They're actually better, but they're nothing like it.
Yeah.
And what you get in an AM process is quite different to a casting or a welding process where the solidification conditions are different. Going to your particular point, yes, indeed, you can optimize the composition of the wire to match the solidification conditions that you get in an AM process, which are not the same as a.
Yeah, I wasn't suggesting that they were. It was just that did the process require the?
It doesn't, no. So you can deposit any wire actually.
Yes. So I mean, when you're given a specification as to what you've got to produce.
Yeah. Well, what we're trying to encourage industry to do is to provide us with requirements, not materials. So I need it to do this and this, and then what I didn't show here, you saw the video with the two wires actually. We can mix wires, make any composition. Actually.
Yeah.
So it's rather more powerful than just taking what's around.
Yeah. And does the microstructure, presumably it's not a homogeneous microstructure because of the, if you like, the lines between each deposited strand? That's
true if we don't include any other process. So what we push quite a lot is in process mechanical work. So we put a layer down, we mechanically work it, then put another layer down which thermally treats the previous layer that's been rolled. When we do that, we get a very uniform, homogeneous, small equiax microstructures, which are ideal engineering application. But you do often need this kind of ancillary process.
Yeah, that was going to be my question really about the directionality of the properties. I think it's a discussion really for all processes and manufacturing methods, that it's much easier to work with a series of requirements and fitness for purpose, as opposed to a defined process or a defined alloy. I know that's certainly something our foundries sometimes struggle with. We're presented with something and told which alloy to use, and then they'll know that it's not going to be very easy to cast or very easy to process. So you say there aren't really directional issues, and obviously you're using this technology for some very demanding applications. Sorry, go on. Yeah.
I was going to say, I didn't say there wasn't any issues. I said we have ways of dealing with it.
Okay, fair enough. Yeah. And the other question I was going to ask was about energy. Yeah. About the energy intensiveness of this process compared with other things. I mean, obviously you're taking out some of the aspects in terms of tooling, but there's still a lot of energy going in, presumably to heat the metal. Have you any sense of how it compares at this stage? And secondly, is that something that your customers are asking more about?
So we know precisely what it is, yes, because customers ask about it all the time.
Yeah.
But the biggest thing, of course, is that most of our processes are much more material efficient. So actually the big saving is in the embodied energy of the material that's reduced. And so if you're looking at a titanium part, then it's roughly 500 megajoules per kilo of titanium that's required to manufacture that, which is a huge number. So if we reduce the amount of material, then it's very energy efficient. In terms of the energy efficiency itself, if we use a standard plasma-based process, the energy efficiency in terms of the amount of energy used to melt the material we deposit compared to the minimum amount needed to melt that metal is about 25%. With the recent process, the CWMIG process, it's about 80%, because effectively we're melting just wire, we're not melting much of the substrate.
Okay, thank you. Yeah, okay. Any other questions at this stage? Or comments? Oh, Ian, I think you'd like to come in.
I find it quite fascinating, and congratulations on having achieved so much. It was truly impressive. I'm interested in the whole interface between yourselves and industry, and the point at which you make decisions to establish a company, to get outside investment, and how the whole relationship works. It must be extraordinarily difficult at times to know at what point you do bring people from outside in and it ceases to be just a university exercise and becomes a joint venture. And in addition to that, there's the whole question of the money, where it comes from and at what point. I'd be interested to know, for instance, how much you think this whole venture has cost since sort of the start right through to where you are now.
Okay, so taking the first point about when to do it, we did try to do it earlier actually. So I mean, I think the answer to your question is we were probably 10 years into the program and had solved most of the issues, but there was no supply chain, and I tried to get the university to set up a spin out at that point, but the way the university was set up, it didn't support that kind of activity, shall we put it that way. So then we went through this period of looking for partners, and partners are rather reluctant because they, if you go to a robot manufacturer, for example, they're not very interested because the numbers are low. They're much more interested in selling 1,000 robots to Jaguar Land Rover or something than a few for additive manufacture. So then we literally had to set the company up ourselves and try and find an investor. And that was quite a frustrating process, I must say, in particular because a lot of our IP was bound around know-how rather than patents. And what I found was investors, particularly venture capitalists, really can't see past patents as being IP, but actually it's much broader than that. So trying to convince them of the value was a bit of a challenge. And then, as you saw in the end, we ended up with a technology investor rather than a venture capitalist, which is good and bad, of course. So they provide a bit of a comfort blanket, actually, which maybe is not such a good thing. I've forgotten the first question.
But just how much you think the whole thing's cost?
Oh yes. So, well, as I said, in terms of the research, probably around about 30 million so far in the university, and in the company we've had, I would say probably 6 or 7 million. It's not big numbers really, considering what we're doing, particularly with regard to the investment side of things. One of the issues we had actually, or have, is during this period when we developed the technology, other companies set themselves up to do the same thing. They copied us basically, and they just put in place a company with a robot and a welder and said, here's a WAAM system. And of course, they didn't have any of the know-how. So in reality, it wasn't a WAAM system, it was just a robot and a welder. And then when we did get to market in 2021, 22, we found it was quite hard to penetrate the market because these other companies, despite not knowing anything, had a good position because they were there first.
Thank you. And apologies, I got a lighting engineer has just turned up, so I'm going to have to flee.
Okay.
Forgive me.
Thank you.
Thank
Well,
you
we're
very much.
approaching. Thank you, Ian. We're approaching 8 o'clock anyway, which is when we normally try and wrap up by. So I think on behalf of everybody, can I thank you, Stewart, for taking the time to talk to us. Particularly, I should say, at a time when Stewart's working with an interim CEO, because they're recruiting for a new CEO at the moment. So I have an interim, but I can imagine that's you know, quite a challenging time when you're like a man down effectively, or a person down, and also trying to recruit, which is incredibly time consuming, as we all know. Thank you also to Eloise, who is behind the scenes looking after everything for us from a technical point of view, a technological point of view, making sure the system runs tonight and recording it for us. I invite you to join our next lecture, which is in April. Another person from Cranfield, actually this time it'll be Professor Mark Jolly, who'll be talking to us for our evening session then. And obviously those of you in the founders will probably meet you at some of the lunches and events over the next couple of months. So thank you, Stewart, again, a sort of a silent clapping applause for you. But again, thank you very much for taking the time to join us tonight. And yeah, and maybe see you at Cranfield when some of us are there in the future. Thank you.
Yes. Thanks very much.
Thank you.
Thank you very much.
Cheers, everyone. Take care.